So here we go, Chapter 5 on gases. First thing we're going to do is check out the difference in um, solid, liquid, and the gas state. So you notice in the gas state, molecules are very far apart, moving very quickly, and there's a lot of space there that we can actually use up by compressing those molecules. In the liquid and the solid states, the particles are just about touching, so they're not compressible at all. There's a lot more motion in the gas state, and much less as you go to the liquid and the solid states. You notice in the solid state, the particles line up pretty evenly and regularly, yet in the liquid state, even though the volumes look pretty much the same, they're not lining up very well at all. Okay, next thing we have is just let's focus on the gas properties. So gas properties, no constant volume or shape, very low densities, very compressible, and they have high kinetic energies. Gas volumes are affected by three different factors: pressure, temperature, and change in the amount of gas. Because of this, we have to always calculate what the gas volume will be if any of these conditions change. Well, the first thing we want to do is check out air pressure. Now, air pressure is the weight of the air directly above you to outer space, that is. It's greatest at sea level because there's simply more air above you going to outer space. As you go up in elevation, the air pressure becomes less and less. So therefore, air pressure increases as you go down towards the surface. So in this country, our lowest air pressures are in cities like Denver or Santa Fe, where they're very high in altitude, whereas our highest air pressures are in places like deserts. In fact, I think our highest air pressure normally is in Death Valley in California. Now, air pressure is measured by a barometer. So let's check out a simple barometer. So here we have a dish with mercury in it, and there's an inverted tube that had mercury in it as well. You notice that most of the mercury is staying up in the tube. And what's keeping the mercury in the tube is the air pressure. Now, the air pressure is pushing down on the surface of the mercury. You can see the arrows there, trying to keep the mercury in the tube. Gravity, on the other hand, is trying to pull the mercury out of the tube. Now, this gives rise to our first pressure unit, which would be a distance unit. So at sea level, the air pressure is great enough to maintain a column of mercury 76 centimeters high. Now, if you took this barometer up to a higher elevation, you would notice that the mercury would start to come out of the tube. And if you brought that barometer off the mountain, the mercury would go back up into the tube. So this gave people a way to measure air pressure, which was very helpful, especially for ships at sea when storms would come up. Because as we know, with storms, we have low pressure areas. In nice weather, it's high pressure. So with a ship at sea, then, a storm could come up very rapidly and they have no place to hide from it. And so to know that the storm is coming would be most beneficial to them. Now, the units of pressure that we're going to check out now, it's about 5 or 6 of them. And these are all what we call standard pressure, and they're all equal to each other. So the first one we have is an atmosphere. That's our largest pressure unit. So 1 atmosphere is equal to 760 millimeters of mercury. That's also equal to 760 torr. Now, the Italian scientist that invented the barometer was called Torricelli, and that's where we get torrs from. In the metric system, we use kilopascals, and so standard pressure would be 101.325 kPa. In this country, we have a psi, a pounds per square inch, and standard pressure is 14.7 psi. Now we want to take a moment to do a couple of conversions because you're going to have to do this in some of the problems. So we're going to take a look at 2 of them. And the question is, convert 1.10 atms to millimeters of mercury, and then also convert it to kPa. All we have to do is know the 2 conversions, and here they are. So why don't we stop for a second, and you can pause this, and you do the conversions, then we can go back and check out your answers. Okay, let's check out the answers now. So for the first one, you see, we'd have 836 millimeters of mercury, and the second one would be 111 kPa. Next thing we want to check out is, what about a container that has a gas in it? Does it create pressure the same way that the air does? And the answer is no. So we're taking a look on the left here at a piston cylinder setup. We have the gas trapped inside the cylinder. Now the pressure in that cylinder is created by the gas molecules causing collisions between themselves and the walls of the container. So here the key word is collisions. Anything that would increase the number of collisions or the force of those collisions will increase the pressure. So how do we measure the pressure of the gas that's confined like that? We don't use a barometer. Instead, we use manometers. And here are two simple manometers. Now you might have noticed one on the left there. You see these kind of valves on large tanks of gas. And here on the one on the right, we have a blood pressure cup, which is also called a sphygmomanometer. And so the blood pressure cup works by pumping air into the cup enough so that it cuts off the blood flow. And then the person listens for the blood flow to resume as they let the air out of the sphygmomanometer. We also have two kinds of manometers that we could see in a lab. One is called the closed-end manometer, and the other is an open-end manometer. So let's start with the closed-end one. So we start off with the gas in the container. You see that yellow gas. Now that gas is causing pressure and is trying to push the mercury away from itself. See how we have the black arrow showing you that. So the pressure is going in that direction. And because it can't get through the stopcock, it's pushing on the mercury. Now the pressure of that gas would simply be the height of the level of mercury. It's the difference in those two levels. So you see how the H is represented here. So the pressure of the gas is simply the height of it in the tube. Now the difference between the closed end and the open end is that with the open end, we have the air pressure to contend with. Now the gas is still creating pressure in that direction, but now the air is also creating pressure in the opposite direction. So the pressure of the gas in this case is going to be the sum of the height difference and the atmospheric pressure. You're probably going to see a couple of questions like this in the Connect assignment, and I'm sure there's going to be one on the exam as well. All right, now let's take a look at that same condition that we had a moment ago with the piston cylinder apparatus. So next question is, what would happen when the pressure on the piston is doubled? What do you predict would happen? Well, let's check it out. If we were to double the pressure, let's say it went from 100 kPa to 200 kPa, the volume would be cut dramatically. Now you notice that the new pressure is going up from 100 to 200 as well, and that's because the particles now are much closer together, and so the number of collisions between the particles and the walls of the container, the number of collisions has increased dramatically. In fact, they probably doubled. So what we noticed then is the volume went from 1 liter to a half a liter when we doubled the pressure. It's kind of like an inverse relationship. In fact, that's exactly what we have. Now, if I take my pressure and volume from my first condition and multiply them together, I get that. It's going to call those ones P1 and V1. And if I do the same for my second conditions, you notice I get the same answer. I'm going to call those P2 and V2. And since they both gave me that same number, I can then say that these two equal each other. And this is our first gas law. P1 V1 equals P2 V2. And this is called Boyle's law. So that's our first gas law. We're going to have a few others. Now, next situation we're starting off with, we have two beakers, a large beaker that has some water in it and a balloon. And sitting on top of that balloon is a smaller beaker that has water in it as well, so it's putting weight on the balloon. And that large beaker is sitting in some ice. And we're starting off with the volume of the balloon being 150 milliliters and the temperature being 273 Kelvin or 0 centigrade. So we're going to find that when we deal with gases, we have to have our temperature in Kelvin degrees. So what will happen to the volume of the balloon if the beaker is heated to 373 degrees or 100 degrees centigrade? Well, let's see. Wow, notice how large the balloon has become now, so much so it's pushing that beaker with water in it right out. So let's see, what would our new volume become? Could you have predicted what it would become? Well, it would become 205 mLs. And this gives us Charles' law, which is V1 over T1 equals V2 over T2. So what we say here is volume and temperature are directly proportional to each other, but you must have the temperatures in Kelvin degrees for this gas law to work. So you must remember that. And you can see by just plugging in the data, we would cross multiply and solve a V2, and we would come up with 205 mLs. Right, the next gas law we're going to take a look at will involve a container that has a constant volume, and now we're going to be pumping more air into it. So we're starting off with 1 mole of gas in the container, and the pressure then is 100 kPa. Now, if I pump in some air in there, I can get the pressure to become 200 kPa. How many moles of gas would be in there now? Right, you guessed it, 2 moles. So you notice I doubled the pressure by doubling the number of moles of gas. And if I put in more gas, I could probably burst that container. And let's say that it took 600 kPa to burst that. How many moles of gas would be in this now? Well, it'd have to be 6 moles. And we can answer that very easily by looking back at the first diagram. So here we have another gas law relating pressure and the amount of the gas. Now the amount of the gas is not in grams but in moles. So we have P1 over N1 equals P2 over N2, another direct proportion. And this one is called, and you might recognize this fellow, we've seen him before, Avogadro's law. Even though it's not that important whose law is whose, it's really the application of them which are going to be asked to complete. Now, next situation we have is a container again with a constant volume, but this time you notice we're taking its temperature. So it's at 300 Kelvin and we have 100 kPa. So what would happen to it if I were to heat this? What do we see happening? To make the pressure go from 100 kPa to 200, I have to double my Kelvin temperature. Now you notice I'm not doubling the centigrade temperature. In fact, the centigrade temperature is going up more than 10 times. But the Kelvin temperature is only doubling. So the increased pressure is due to those particles moving a lot faster, creating more collisions and more violent collisions with the walls of the container. And eventually we'd get to 500 kPa, and that would burst the container. Now, what temperature do you think we needed to get to that? Again, if we compare our first diagram to this one, we can see that the pressure would go from 100 to 500 kPa, so the temperature must be going from 300 to 1500. And this is going to give us the law of Gay-Lussac, which is the relationship between pressure and temperature, another direct proportion. Now we can put all these gas laws together. I'm just going to put them all down here again for you. We can combine them all together in what we call the combined gas law, which would look like this. And this is really the only one we have to use for all of these problems that we're going to see in this lesson. If any of these factors aren't changing or they're not even mentioned in the problem, we're just going to eliminate them from the formula. So let's check out the first problem. So the helium in a 250 milliliter balloon exerts a pressure of 800 millimeters of mercury. What pressure will the mercury exert when its volume is reduced to 125 millimeters? So the first thing we want to do is copy out the data and label it. This is real important so you know exactly what you're doing. Now you don't have to go back up and read the problem. Next step would be to write the gas law. So I'm going to write down the entire combined gas law, but then I'm going to cancel out any factors that are constant or weren't mentioned. Now in this case, the temperature and the number of moles weren't mentioned, so I'm going to cancel them right out. And then what am I left with? I'm left with the part of the gas law that I have to use. Now you may recognize this as Boyle's law, but that isn't that important. So I'm going to now solve for my unknown, which is P2. And I do that by dividing by V2 on both sides. I plug my numbers in and I get 1600 millimeters for an answer. Now one way to check on this is to see how the volume has changed and predict what will happen to the pressure. So we see that the volume went down, so the pressure should go up, and this seems to fit. Alright, let's try another problem. Here we have a balloon with a volume of 120 milliliters at 17 degrees centigrade. What will the volume become when the temperature becomes 34 degrees centigrade? So we copy out the data and label it. Write down the gas law, cancel out the units that we don't need anymore. Cancel out the factors that we don't need anymore from the equation, and solve it. So let's see if you can solve this one on your own. So I might want to pause at this point in time, and then come back and see the solution. Okay, here is the solution now. So I copy out my data. You notice that I convert my centigrade to Kelvin. If you didn't do this, you would have got the wrong answer. I'm writing down my gas law. I'm going to cancel my constant factors. In this case, it's moles and pressure. That leaves me with Charles' law. I'm going to take Charles' law and solve it for my unknown. So I'm going to cross multiply. This is what I get when I cross multiply. And now I'm going to divide the T1 out of there. So I wind up with V1 T2 over T1 equals my unknown. I'm going to plug in my values, and I get 127 mLs for an answer. And that's what I would have expected, because if the temperature goes up, then the volume should go up. So how did you do? All right, let's try another problem. Now in this case, we're going to be using more factors. So here we have a gas occupying 225 milliliters at 27 centigrade and 100 kPa. What volume would the gas occupy at standard temperature and pressure, STP? Now standard temperature has to be 0 centigrade or 273 Kelvin, but it can be any of those standard pressure units we saw early in this lesson. So let's copy out the data and label it. So we have a lot of data here. And all right, now I'm going to write down my gas law. In this case, the only thing I'm going to be canceling out is N. That's what I'm left with. Now it's just a larger ratio. I'm going to cross multiply and divide. And this is what I have so far. Now I'm going to finish this up on the next slide. So here's where I left off. I have my gas law, which I've cross multiplied. Now I'm going to solve for V2. So to get V2 by itself, I have to divide by P2 and T1, and it'll cancel out of there. And now I finally have it. So at this point in time, I plug in all my values and then solve it. And you notice that all the units will cancel except for mLs. And I get 202 mLs. So now let's take a look at another way we could do this. This is called the logic method, where we just figure out what will happen to our unknown, whether it'll get larger or smaller, and then we just make fractions out of the data to make this work. So these are the same three problems that I just went through, but looking at it logically. So here was the first problem, and there was the data. Okay. Now, here was how we figure what's going to happen. If the volume goes down, which it is, then the pressure has to go up. And that tells us that P2 has to be greater than P1. So P2 is going to be bigger than 800 millimeters. What I'm going to do is make a fraction of my two volumes that's greater than 1. So I'm going to put the larger volume on top, smaller one on the bottom. Then I'm going to multiply this by P1. So when I do that, what I get for an answer? I get the 1600, just as I got using the formula. This is why it's called the logic method, because you logically figure out what should happen to your unknown, and you just make the math work for you. So let's apply this to the next two. So this was the second problem that we had. It was our data. So see how the temperature is going up. Okay. If the temperature goes up, then the volume should go up. That means we need a fraction greater than 1, just like we had before. So my fraction would be 307 over 290. That's greater than 1. And I get an answer of 127 milliliters. And we can even apply the logic method to more of the gas law, as we saw in the third problem. So here's that gas law again, and here's our data. In this case, we'll take each change separately and see what would happen to the volume when each of these changes happens. So the first thing we'll look at is pressure. If the pressure goes up, then the volume should go down, which means we need a fraction that's less than 1 out of my two pressures. For temperature now, since temperature is going down, I need a fraction also that's less than 1 for my two temperatures. So then when I set them up, it would look like this. And there's my answer. Okay, looks pretty good. All right, so this is the end of the first lesson. So what you should do at this point in time is either try some of the problems out of the text, or you could even go to the Connect assignment and try some of those.